Jetzt mit Ton. So. Ja? Das ist der Bruder von Siegfried Steinkauf. Jetzt mal. Und ein Cousin von Balduin Bartkauf. Brexit? Ja. Ja, es kommt halt immer verzögert. Ne? Okay, funktioniert. Stark. Aber der Stream läuft schon ein bisschen. Ich weiß halt nicht, wie gut. Nee, ich habe das auch mal gehabt. Mal ist per Kabel verbunden. Das ist glaube ich, alles gut. Ich weiß nicht, warum das nicht abgeht. Weil es ist nicht GDPR. So, good afternoon, everybody. Let's begin. Last time we did two main things. The first one was to show that spherical collapse in a Gaussian random field is forbidden. Second was that I started introducing kinetic field theory as a theory for structure formation. Now, at the end of the lecture, there was the remark by one of you that the fact that equal eigenvalues have zero probability does not mean that that almost spherical collapse should not be possible. So I was planning, which is a very valid remark. No, even though equal eigenvalues in the collapse may not be allowed, almost equal eigenvalues may have a finite probability. So I was planning to design a problem sheet for you, right, to calculate mean axis ratios, right, to see that the mean axis ratio is substantially different from 1. But then it turns out to be so difficult that I'd rather not put this on a problem sheet. But this made me fall behind in designing the problem sheet. So, okay, you will get a problem sheet, but with a little bit of delay. All right. This was the first point. The second point was that I started introducing the main ideas of KFT. And this is where I wanted to restart today with a little bit of notation first. And very much of the notation is just meant to avoid indices, writing very many indices. You'll see about that. But do you have any questions before we restart? What is it? What? Yeah, not inside. All right. Kinetic field theory. Did you see the lecture notes grow? Are you watching the lecture notes grow? So this is the main idea, or the main subject of the lecture, kinetic field theory. We used to abbreviate this with KFT, which is not to be confused with KFC. This is something completely different. And I mentioned last time already that the idea is very, very simple. Same picture as last time. So we start with some initial slice in phase space, and we launch a trajectory at some point, and we follow this trajectory over time with the Green's function for the Hamiltonian that we have. We end up here, and we plant we plant trajectories everywhere on this initial slice of phase space with a certain probability distribution, right? So you imagine this domain in the initial phase space is covered with some probability distribution, and we transport this probability distribution forward in time with a Hamiltonian flow, and this will allow us to read off properties of the final particle distribution or the particle distribution at any time t by suitable means. That's the idea, right? So we need, and this will be one of the main contents of today's lecture, we will need a probability distribution for the initial state. We already know how any point or any trajectory starting at any point in phase space will look like, because we know the Green's function. And then combining these two notions, right, the initial probability distribution and the Green's function for the trajectories, we set up a generating functional. And the generating functional looks essentially like this. I'm interested in the probability for finding a particle at position x in phase space at time t. I'm splitting this up into a probability distribution for ending up at time t, for ending up at position x if I start at position xi, times the probability for starting at xi. This is just Kolmogorov. Huh? I need to integrate over all initial positions here. Then I get the final probability. And since I have to do with classical particles, I know that this probability distribution here is essentially a delta distribution. Right? It's going to be non-zero if the points xi time at the initial time, 0, and x at time t are connected by a solution of Hamiltonian equations, and it has to be 0 for any other path. So this is going to be, in a slight misuse of notation, delta of x minus xi, where this is very shorthand notation for saying, let me put it like this. Okay, if the trajectory equals the solution of Hamilton's equations x bar beginning at position xi in phase space, then the delta distribution is non-zero, and otherwise it will be. This is because we have classical particles, that's our advantage. And then with this probability distribution, we set up a generating functional for the entire n particle system here, which looks like this. I'm integrating over all possible trajectories. The probability for these trajectories here ending up at point x in phase space. And now I multiply this with an exponential function that I introduce with a generator or source field J, whose only purpose it is that I want to take derivatives with respect to J in order to bring factors x down to make averages of x or x squared or x cubed or whatever you want to have. And so the only purpose of introducing J is that I want to take derivatives with respect to J as you know it from thermodynamics, for example. All right, now this is a path integral, right? Because we are integrating over functions. It's going to disappear very quickly, because if you now insert the above expression for the probability for ending up at point x, this delta function picks out of all possible paths just x bar, and what remains is an integral over all initial positions in phase space times the probability distribution for position xi in phase space to be occupied. And now e to the power of I j x bar. And I'm abbreviating this. This is my initial phase space measure as d gamma. And so we have our generating functional for kinetic field theory as a functional. I'm going to say a few more words about this. The functional of source field J, which is given as d gamma e to the power of I j. This contains the complete information about our n-particle system, regardless of whether it is in equilibrium or not. And now I need to say a few more words about what this notation should mean here. First of all, of course, the x bar is going to change over time. Right? The particle is propagating forward and its position is going to change with time. So this scalar product here should contain an integral over time. Because if it didn't, we would integrate over the particle trajectories to some final time, and we would not be able to extract any information about the change of any statistical quantities with time. So this is meant to contain an integral over time and here I'm writing integral 0 to t over dt prime, and the field J will depend on time and x bar will depend on time. Now I'm writing some kind of scalar product. I'm going to have to specify this as well. I'm going to write some kind of scalar product with a dot here. Right? But I wanted to make explicit that this scalar product up there contains information about time. And it should, because we want to study the evolution in time of statistical properties that we want to derive from Z of J. All right, now J is a field. It's a function of time. And this means that any derivatives that we are going to take with respect to J later are going to be functional derivatives. Okay, but that's the consequence that we want to have a non-equilibrium theory. It will depend, any statistical properties will depend on time, and so we will have to take derivatives with respect to functions of time, functional derivatives. Okay, fine. Now, suppose I wanted to have the average position, right? I would have to do the average position of a particle, I mean. I would have to calculate d gamma times x bar. And this would be the average of x bar, average over the only probabilistic information that we have, or only stochastic information that we have in the system, namely average over the initial probability distribution. How do I get this now? I'm going to evaluate this at J equals 0. And this will be the average particle position at time t. And I'm going to write this as minus I functional derivative with respect to J applied to the generating function. And as you know it from thermodynamics, for example, right? If you want to know the mean particle number in a grand canonical description of thermodynamics, you would take the grand canonical partition sum, from thermodynamics and take a derivative with respect to the chemical potential. Same procedure appears here. Now, suppose you wanted to calculate a correlation function and you would apply two of these, or a variance of the position. You would apply a square of this operator and so on and so forth. This is going to come later. All right. Now, I want to introduce mathematical structures that allow me to write the bundle of trajectories that I'm studying, right? Trajectories starting from all points in phase space as one mathematical object. And usually I would enumerate the particles with an index I from 1 to n. N is a very large number. And I would get, for all of these particles, trajectories xi or x bar I labeled with the index I. Now I'm forming a tensor product with the unit vector EI. It's a unit vector in n-dimensional space. And I call this x bar of t without an index here. So in other words, you have one long mathematical structure where for each particle, its trajectory is attached to a kind of comb. I think of that like a long vector which has all the trajectories attached. This is just to save ourselves from writing particle indices all the time. All right, now also this should simplify the notation and therefore make more physically clear what is really going on. Yes. So the tensor product means that for each object here, you assign another object here. So the EI is the unit vector in n dimensions, right? So it's 0 everywhere except for for ith component. It's the Cartesian, ith Cartesian unit vector. So now with the Green's function, we can write down the whole bundle of trajectories in one step. We can write, this is now a Green's function for all particles together. These are the initial phase space positions in one object together. And then you can write let me write F here. F of t. So I want to be able to write the complete bundle of trajectories in this way. And this means that the curly G here just has to provide a copy of the Green's function for all particles. So I can write the G of the 2 times t and t prime as the Green's function for a single particle, which is a 6 by 6 matrix, right? Because we propagate each particle through 6-dimensional phase space. And now I have to take this for all n particles. Okay. I mean, I agree it takes some time to get used to that, but I think once you are used to it, it just makes all the equations much easier. Yes. I sum over all of them, yes. some convention applies. All right, so that would be the Green's, yeah. No. I mean, we derived this Green's function before. So with the Seldovich trajectories, we could write the Green's function just in this way. We have the effect of the force, the gravitational force on the trajectories here. We derived this before, and we solved the Hamiltonian equation in this way. Okay. All right, so we have this curly G here, and then we need a suitable force vector here, which now must collect all the forces on all the particles. And this looks like the force on any single particle. So I have to take the gradient here with respect to the position of particle I. And this will act on particle I only. And the complete tensor of forces acting on all the particles together is now this object here. All right, so I know what the trajectory should be like. So I know what I should insert in here. So this means that this generating function here contains both the information about the dynamics, because the Green's function solves our equation of motion, and it contains information about the probability distribution of initial positions, because that is contained in this initial phase space measure here. And all I introduced here, right, with this tensor product notation, is just to keep the overall notation as short as possible. So what do we need now? We need the probability distribution for the initial particle configuration. And that's going to be the next step. But before we move on to that, do you have any question concerning this? Yeah, we could drop it as well. It's just there for conventional reasons. And we could start writing the phase without that here. But then later, when we speak about density operators, I would get a factor of I in there anyway from a Fourier representation of the delta distribution. And so you just shift it around then in the formalism. So all in all, we found it more convenient to have it in the original definition and then not in what is coming. Yeah.
Scalar product and mass product
yes. Yes, let me say one more word about the meaning of the scalar product now with these tensorial quantities here. So we already do have a normal scalar product in there, namely the scalar product between the field J and the trajectories x bar. So let us look at what this should mean. Now, of course, we need one representative of the J field for all the particles. So the J gets the same structure how do I do this now? And I need a vectorial component of J for the configuration, space position in phase space, and one for the momentum. And they will depend on time. So I have 6 components of J for all particles. And I bundle all of them in this way into a tensor. And now I have to take the scalar product with U bar, and it's the trajectory in configuration space of particle I. P bar, that's the, to take another particle index to make this clear here. So this is the phase space trajectory for particle J, split into Q and P times Ej. This is J, this is X bar. All right, and now you define a scalar product as usual. You take the scalar product of these two. This gives you delta Ij. You get a scalar product of these two. So this is going to be JQi times Q bar I plus JPJ times P bar J delta Ij. So yeah, in other words, that's going to be, that should be J, that should be I, sorry for the mess. So this is JQi, now just the Euclidean scalar product, Q bar I plus JPi times P bar I. Okay? There was a question somewhere. Index confusion. All right. Same with the product with matrices. So suppose you take now the Curly-Green's function. Let's do it like that. So this means that the matrix Green's function will have to act on all the trajectories. So this is G of t in 0 times a unit matrix representing all the particles times phase space position of the ith particle. Yeah. All right, now you get G of t in 0 times xi. Right, this propagates the ith particle forward. Now you have tensorial times unit matrix times EI. So you get this. Good? Okay. Now let's speak about the initial conditions. Now we are going to make use of the assumption, and we justified this assumption before, that we start in some way we have to clarify from Gaussian random field. And I use the central limit theorem to justify that. Say that whatever process created the structures in the universe, could have been inflation, for example, will superpose many, many density fluctuations of, for example, a vacuum quantum field. So that the final density contrast that you observe in the universe will be a superposition of many independently drawn, but identically drawn fluctuations. This will lead to a Gaussian distribution. This is one justification from the central limit theorem. The other justification is that we have no indication from observing the cosmic microwave background, for example, as the earliest empirical evidence of structures in the universe, that there could be anything non-Gaussian to it. So let's start with the Gaussian random field. And I want to quantify this Gaussian random field by the velocity potential. And I want to use at an elementary basis that I have a velocity potential, psi, such that, do you see that? Such that the gradient of psi is the initial momentum. And the psi will be a Gaussian random field by assumption. And we will know, or we do know from the continuity equation, that the density, the initial density contrast here, and psi will only be initial, but the initial density contrast and the Laplacian of the velocity potential are related by this Poisson equation. So the initial density contrast is going to be a Gaussian random field. Then the velocity potential will also be a Gaussian random field. And in all what is following now, while we are looking at the initial conditions, I will drop the superscript I. Right, so from now on, we are dealing with statistics on the initial phase space only. Because if I write the superscript I all the time, then I use much too much chalk on that alone. All right. So I'm assuming that I have an ensemble of n particles. And I'm looking at the values of the density contrast at the positions of all these particles. So I want to assign density contrast to all of these particles. And I want to assign initial momenta to all of these particles. So the basic Gaussian variable, the basic Gaussian variables that I'm going to assign to all my particles will be the density contrast at the particle positions and the gradients of the velocity potential at this particle. And so I'm imagining I have this Gaussian random field, which could be either the density contrast or the velocity potential. I'm picking out one position where I later want to place a particle with a certain probability. And I'm asking, what is the density contrast there and what is the gradient of the velocity potential at this point? And then I create a huge data vector with all these entries here. Okay? So I have this set of numbers. All of these will be drawn from a Gaussian distribution. And I'm combining them into a huge data vector, which I imagine contains all the density fluctuations first. And all the gradients of the velocity potential then. All right. And then I know what my probability distribution looks like. My probability distribution for this data vector here. This will just be a Gaussian. And so I know that the probability distribution for the data vector D is going to be 1 over a glorious normalization factor, which now contains 2 pi to the power of 4n. Because for each of the n particles, I have 4 quantities. Gradient of the velocity potential and the density fluctuation. Then there's going to be a covariance matrix whose determinant I need. This will be a 4n by 4n matrix. Unfortunately, we will never have to invert this. And then we'll have the usual quadratic form for the Gaussian distribution, which look like this. And the covariance matrix C, this is going to be the average of the tensor product of D with itself. In other words, that's going to be the matrix form collection of all the cross correlations between all the numbers that we have in this vector here. Will contain the cross correlations of all the density fluctuations, cross correlations of all the gradients of the velocity potential, and cross correlation. All right, so far so good. Do you agree so far? And we have a collection of Gaussian random numbers. They are Gaussian by assumption, and the assumption is based on the central limit theorem. So this collection of numbers here must follow this Gaussian distribution. And of course, we are postponing the problem of determining the covariance matrix to some later point. All right. But this is not exactly what we wanted to know. What we wanted to know was not the probability distribution for some density fluctuation or for some moment, for some gradient of the velocity potential. But what we want to know is the probability for a phase space point to be occupied. So I want to know what is the probability distribution, not exactly for this vector D here, but for the collection of phase space positions x1 to xn. And there's a slight difference between the two, which gives rise to a subtlety that you can almost always ignore. But let me show you the problem, or let me first discuss the problem. We don't know yet what these positions qi are. We are just assuming that each of these particles has a position qi. We want to know with what probability will I put a particle at position qi in configuration space. And I'm assuming that we are sampling this density field here with a particle. And in other words, we want to have a probability for placing a particle at position qi that is proportional to the density at this point, the density at any point. The density at any point will be proportional to 1 plus delta r. Proportional to 1 plus delta. That's the density. So the probability distribution for finding a particle at any position should be proportional to 1 plus delta at that position. Now, of course, if I integrate over a finite volume, this probability has to be 1, so I need to divide by the complete volume that I'm averaging over, or that I'm, the complete volume that I'm filling. And this is going to be the probability distribution for finding a particle at position q, or let me write at position qi, given the density contrast field at the position qi. Right, so I'm assuming that. Right, there's a conditional probability for finding a particle at position qi if the density contrast there is delta at position qi, which I abbreviate as delta I. Yes.
I really get my probability and probability line as 1 plus or kind of certain.
Well, delta can be negative, right? So I need to take into account that the probability can be higher or lower than average, depending on whether delta is positive or negative. And the integral over all of the density contrast should be 1. If I just use delta instead of 1 plus delta, it would be 0.
That's delta, but the probability that we have this. And so we find our vector D as and first our deltas and then our gradients. The first half the layer D contains all the different deltas.
Mhm.
Why don't we use the probability of these deltas?
That's what we are doing.
And now as well for
That's what I'm doing. So the first thing is that I determine the probability for having a certain density contrast somewhere. And then I'm asking the question, okay, given that density contrast at any position, what is the probability of sampling it with a particle? Right? So this means Poisson sampling of the density field. And this means the random distribution of the density field itself. All right, then I need a probability distribution for the momentum of the particle. And this is simple, right? Because once I know what the gradient of the velocity potential is, I know that the conditional probability for finding the particle, for finding a particle momentum pi must be the delta distribution of pi minus blah blah I psi. So that's the probability distribution of finding pi given the gradient of the velocity potential. All right, and now I can assemble the complete probability distribution. This means we have to marginalize over all variables that we are not interested in. So I want to know what is the probability distribution for the collection of particle positions and momenta. That's what we need, right? This is what we need to enter into the generating functional that is now gone, and allow me to drop the vector arrows. So what is this? That's going to be the probability to find a particle given that there is a density contrast delta r. Probability to have the particle have the momentum pi given that the gradient of the velocity potential is grad I psi. Then I have the probability distribution for the complete data vector that I set up above, that's the Gaussian there. Now I need to integrate over all the deltas, and I need to integrate over all the gradients of. That's going to be it. No more than that. And it's going to be much easier to deal with everything what is coming, in particular to deal with these integrations here, if we now switch to the characteristic function of our probability distribution P of D rather than the probability distribution itself. And so now I'm going to use that P of D is the Fourier transform of some characteristic function. This will be a characteristic function of a Fourier conjugate variable to the data vector D, which I call S. And this is going to be multiplied with a Fourier phase that contains the ordinary Euclidean scalar product between this Fourier conjugate vector S and the data vector D. All right, so I want to switch to a characteristic function here for reasons that will become obvious immediately. But since I start out from a Gaussian, I know that the characteristic function is also a Gaussian, which now does not contain the normalization factor, and it does not contain the inverse, but the ordinary covariance matrix. So phi of S is going to be the exponential of minus a half S transpose C times S. Okay? Lovely. Now, I'm going to return now to this probability distribution for the phase space 0.6i. And I'm going to write, this is now an integral over the Fourier conjugate variable S. The delta distribution for the momenta, the conditional probability distribution for sampling particles. Let me just write this as this. And now I can immediately apply the characteristic function. And now I have to integrate over all the nuisance variables, right? D delta and D grad psi. So that's the same thing. Now, again, I'm using rather sloppy notation here because there's a delta distribution for all these particles. And there's one of these factors for all these particles. Okay? But, yeah. So I should write a product over all I. I should write a product over all I. Let me just drop that. The Fourier components are missing because I want to introduce something there. So we still have the Fourier phase, as you say, e to the I S times D. And now I want to introduce something in addition. I want to introduce minus I R times delta. I'm artificially adding a Fourier phase such that I can take a functional derivative with respect to R instead of the deltas here. And of course, if I write it like this, right, the R is a Fourier conjugate variable, conjugate to the delta, to the density fluctuations only. So I'm introducing this, but of course, then I have to take this at R equals 0. Okay. Now, first thing we can carry out is, of course, the integral over grad psi. The integral over grad psi will just replace all the grad psi's in the data vector here by momenta. This is beautiful. So let me write this right away as integral over S. Now, 1 plus delta I divided by V exponential of a half minus a half S transpose CS. Leave alone, right? Nothing changes there. Then I have e to the I S delta times delta. The S delta are those components of the Fourier conjugate S vector that multiply with the delta. Then I get SP times P, all the momenta P, minus IR times delta. We move on. D grad psi is done. Now we need a D delta, and we need to evaluate this at R equals 0. Now I'm going to turn these deltas here into operators. I'm going to say these factors delta I here, or let me just write summarily delta, they are going to be replaced by I times dr. Okay? Now any one of these would pull a delta down, as I need it here. But since this will then be an operator, I can pull it out of the integral and carry out the integrations as if it wasn't there. I promise the result will be very straightforward, almost all the time. Okay, now in order to make use of this operator replacement for delta, I introduce an operator d hat, which is 1 plus I dr divided by v. And once this is done, setting r to 0. A little bit more carefully. This should be the component Ri of the R field. Then we need to take a product over all I and take v to the power of n. Let me just ignore that and write P for the complete collection of phase-space coordinates is going to be the d operator, d hat operator. And with that, we have now covered this factor here. Then I have an integral over the Fourier conjugate variable s for the characteristic function. Now the exponential of minus a half S transpose CS, still completely unchanged. And now you see, now I'm getting a Fourier phase factor for the density fluctuations, which is e to the I S delta minus R times delta. And I'm getting the rest. So e to the I SP times P. And now I need to, and I can, integrate over all the deltas. Because now the delta, the integration over all the deltas just gives me lots and lots of delta distributions, which in summary just replace the first n components of the Fourier conjugate vector S by R's, where there used to be S. Okay? So, but then what is left over is just a Fourier transform. So This I can write as d hat, the Fourier transform of a Gaussian I wanted to say. So now let me write exponential of minus a half. Let me write S bar, okay? Transpose C S bar. Now e to the I SP times P, and the integration over delta is also done. Okay, but now I have a Gaussian integral. And this, of course, I can solve if I want to. But I don't even, because it turns out in most cosmological applications, unless you study very early cosmic structure formation where it's linear anyway, in most cosmic applications, you can set the d hat operator simply to 1 to be evaluated at r equals 0. Yes. You're right. Okay, good. So, yeah, that's correct. But in most cases that are interesting for us, d hat will be 1, and we have to evaluate the whole expression at r equals 0. So most of the time, d hat is going to be extremely simple. And we will justify in hindsight that this is in fact the case. But if I can do that, then this quadratic form is going to be very easy, right? Because then we will replace the first n components of S simply by zeros, right? Because the S bar here, this now has the first n components that are fields, right? The conjugate field to delta. And then come all the momenta. Now, whenever we can make this approximation, and we can almost always do it, then the r's are all going to be will all be set to 0, and then all that remains is a quadratic form that contains only momenta anymore. So under this condition, we just get a Gaussian integral, which is very easy to solve. And if we can't make this approximation, we also get a Gaussian integral, which is less easy to solve. But we can safely ignore that. So the S bar is going to change like that. Then the probability distribution is going to change like that. B to the power of minus n, the normalization factor for the volume. And now we have an integral that only goes over SP anymore, right? Because the rest is gone. And we have exponential of minus a half SP transposed. And what remains is just the correlation matrix of the momenta, right? Because all other components are multiplied by zeros. So now we are back home at the Fourier transform of a Gaussian. And this will just replace the SP by P, turn the covariance matrix around, and add a normalization factor. So that's going to be v to the power of minus n divided by square root. Now 2 pi, how many variables do we have? 3 momenta for each particle, so it's 2 pi to the power of 3n. Now the determinant of the momentum covariance matrix, and now an exponential of minus a half p transpose cpp to the power of minus 1 times p. It's a simple Gaussian for the momenta. If this approximation holds, which it always does, to be proven later. Now, what does this mean here? What does this mean? I mean, this is the collection of all momenta of all particles. Right? So the p's here are these things. Same for the covariance matrix, right? The covariance matrix between different momenta. But we'll see about this later. Right? This is a very beautiful result. Right? So in other words, we can treat the whole system with an initial probability distribution which is Gaussian in the momenta and flat in the position. Okay, because for all the positions, we just get a d3q divided by volume. So it's a flat distribution in configuration space and a Gaussian distribution momentum space. And this also tells you why you can neglect this d hat operator. Because you have very small density fluctuations in the beginning, and the density fluctuations will be much more enhanced by the momenta. And because if particles stream together, they will ultimately create an infinitely large density contrast. So the density contrast later is going to be dominated by far more by the momenta than by the initial density fluctuations. So we can right as well assume that the positions are all equally distributed or with a constant distribution distributed through configuration space. This is, by the way, what all the numerical simulators do. Throw random particles into a box and assign momenta to them. Well, that's fine. Typically, you should take into account that the positions should also be correlated with a momenta. But this doesn't matter much, and we can quantify by how much it does not matter, or by how little it matters. All right? That's going to be our probability distribution for almost all purposes we are going to look into. Careful. This covariance matrix between momenta has to include all the cross correlations between momenta over here and momenta over there. So all the entries in the covariance matrix of the momenta will depend on the separation of the 2 points to which these momenta are attached. It's very important, right? So the CPP in all its components will be a complicated function of position. So this means that we cannot simply move ahead and integrate out all the positions. The dependence on position is going to be complicated. Good. Do you have questions so far? Because of course now we have the business of calculating components of CPP. All right.
Second time when we are about to debate what will already momentum contrast. Okay.
You're right. That's true. I do hope it's correct in the lecture notes. Okay, now let's have a look at one representative entry in the covariance matrix CPP. The full thing is rather complicated. Look, it's going to be the average over P tensor P, and P is the whole tensorial structure of all momenta. So that's going to be Pi tensor EI tensor Pj tensor Ej average. So that's going to be the average over Pi tensor Pj. These are now vectors in three-dimensional space, right? So Pi tensor Pi is a 3x3 matrix which correlates all components of all momenta with each other. But now, tensor EI tensor Ej. This is a lovely matrix here. Right? This is 0 almost everywhere in all its glorious n by n components, except for one, where I equals j. There's a single one standing out in a whole desert of zeros. Right? But this is the structure of this covariance matrix here. Now this I'm going to call CPI Pj. This I'm going to call EIJ. Okay. Now we have the problem of looking at CPI Pj, and to make things easier, I just look at the average of P1 tensor P2 because I can enumerate my particles I like. And so I pick out a particle number 1 at will. I pick out another particle or the same particle at the same will, and I calculate this here. And it's a 3x3 matrix. Now, I'm going to write this in Fourier space. So what do I have to do? Long average. The momentum is the gradient of the velocity potential. So the Fourier transform of the momentum will be ik times the Fourier transform of the velocity potential. Integral over k, e to the I, k times q1. I want the momentum at position 1. So this is why position 1 appears here, and the Fourier transform this way. All right, the same thing for another wave vector k prime, ik prime, psi tilde prime, by which I mean the Fourier transform of psi evaluated at k prime. Now e to the power of I k prime times q2. And the average closes. Now the only two factors in this double integral here that depend on the realization of the Gaussian random field are the psi's. So I get an average of psi tilde times psi tilde prime. That's going to be the power spectrum of psi. So this will be integral over k prime. Now p psi of k times 2 pi cubed delta distribution of k plus k prime. This is the average over psi tilde times psi tilde prime. And remember from last time, or time before that, that this delta distribution appears here because we are assuming that we have to do with a homogeneous Gaussian random field. So a Gaussian random field, that's translation invariant. Okay, now we have I times k tensor I times k prime. So that's minus k tensor k prime. And we have the Fourier transform, or the Fourier phase factor, ik times q1 plus ik prime times q2. Of course, now we can integrate out the k prime dependence. This is going to replace k prime by minus k. Then we get a difference between coordinates, and of course this reflects the homogeneity of the Gaussian random field. Right? It can't depend anymore on the absolute value of either q1 or q2, but it can only depend on the difference between the two. And conveniently, the minus sign is gone, and you get, this is an integral over the complete k-space. K vector tensorially multiplied with the k vector. The 2 pi cube cancels because the integrals over wave numbers contain a 1 over 2 pi cube. Right? So all of this is gone now. Now we have p psi of k, and we have e to the power of ik times q1 minus q2. Okay, this we can deal with, right? So that's rather easy. Now, let me just abbreviate q1 minus q2 by the separation vector r. Okay, so we have to evaluate a quantity like this. And then we do have our momentum covariance matrix. Good. So let me write this down again. Cp1, P2. Now it's going to be a function of r only, and r is the separation between the points 1 and 2, where these momenta P1 and P2 are being assigned. So what is this? Let me just copy that. K tensor k, p psi of k, e to the I, k times r. What are we going to do with this? There's a tensor depending on two wave vectors, but we are integrating over the tensor product of these two wave vectors. What is the result? There is one direction remaining that really means something. That's the direction of the separation between the two particles. That's the only direction that on which the whole tensor that results from that may depend on. And so we must be able to express the CPP as a function of r here by a tensor that depends only on directions defined by r, not by k anymore, because we're integrating over all k. So I'm going to introduce a parallel projector defined by r hat tensor r hat. And r hat is the unit vector into direction r. Why do I call this parallel? Well, because it projects all vectors that you multiply this to on the direction of r. And suppose you take any vector x and you multiply, and you use this definition here. this is going to be the direction of r times the scalar product of r hat times s. So this is obviously the projector on the direction of r. By the way, what's the general definition of a projector? It's an operator whose square is equal to itself, right? Because once you have projected and you project once more, that shouldn't change anything. Is that correct? So, what is this? Well, this is now if you apply the rules of matrix multiplication, that's going to be a scalar product of this vector with this vector here times r tensor r. But this r hat times r hat by definition is 1. So this is, so that satisfies the definition of a projector. Good. Now, where there is a parallel projector, there should also be a perpendicular projector. That's easy now. That's just 1 minus everything that's left, right? 1 minus pi parallel. Does that square to itself as well? Or do we have to normalize it in any way? 1 times 1, 1. Then we have minus pi parallel, minus pi parallel. Okay, and then we have plus pi parallel squared, but pi parallel squared is pi parallel. So it's 1 minus pi parallel and it squares to itself. Aha. So this can rightly be called a projector as well. Now we do the following thing. Now it must be possible to write the CP1, P2 as a linear combination of these two projectors. So it must be possible to write this is A times P parallel plus B times P perpendicular. And we need to find A and B. Suppose this was a vector equation, you would know immediately what to do, right? You would form a scalar product of CP P1, P2 with P parallel, and you would get A. You get a scalar product of CP1, P2 with P perpendicular, and you would get P. So why not do the same thing, right? We introduced the scalar product for matrices last time. What was this? Scalar product of these two. This was the trace of CP1, P2 times P parallel. So we do have a scalar product. We can evaluate A and B immediately. Okay. So let's evaluate this first. That's going to be the trace now of integral over K, K tensor K times pi parallel. Let's write this out right away. P psi of K. Well, that's going to be easy now, right? This is a matrix. This is a matrix by the rules of matrix multiplication. I take the scalar product of the inner vector K with the inner vector R. So that's just a projection of K on R. That's the absolute value of K times the cosine between K and R, of the angle between K and R. I call this mu, right? Because that's the same as the polar angle here. So I get K tensor R times K mu. So it's the trace of K mu. Remember, the absolute value of R hat is 1. Yeah? So I'm getting a K mu from multiplying these two in a scalar fashion. I get now that, just think of the rules of matrix multiplication. So K tensor R is going to remain P psi of K. Now let me write e to the I K R mu. But now the trace is just operating on this matrix anymore. And this gives me another K times mu. Okay? So in other words, the scalar product of CP1, P2 and pi parallel is going to be the integral over all of K space. So that's integral K squared dk d phi d mu divided by 2 pi in parentheses cubed, with mu running from -1 to 1 and K running from 0 to infinity. We get this later. So we have K squared u squared p psi of K e to the I K R mu. That's it, right? This is our function A. B is slightly more tricky, but we'll get to that as well. Okay, now let me write this out. This is an integral over one over 2 pi cubed. But then we also have an integral over phi. But the integrand has no dependence on phi. So the integral over phi just gives another factor of 2 pi, but this time in the numerator. Okay, what remains is K squared from the volume element in polar coordinates times K squared from here. Then we have a mu squared times a function of mu. So we have this integral left. The mu integral, as you will see, is going to be trivial. And here we have K to the power of 4 times p psi. That's the power spectrum now of the density contrast instead of the velocity potential. Remember, we had Laplace squared psi is minus delta. That was the Poisson equation for the velocity potential. In Fourier space, this reads K squared C tilde equals delta tilde, the Fourier component. So this means that K to the 4 times p psi is p delta, and that's what I've used. Okay. Yeah, we are almost done. Now, we need integrals of this sort here. Integral over mu to the power of n times e to the I a mu integrate over d mu. Okay, this is minus I dA to the power of n applied to -1 plus 1 e to the I a mu d mu. Okay? Any derivative of, or any action of minus I dA on this integral is giving you a factor of mu down. And so you can identify these two sides. But this is elementary. just an integral over an exponential. So this is minus I dA to the power of n. Now 1 over IA e to the IA minus e to the minus IA. Here you subtract from a number its complex conjugate. So it's 2 times the imaginary part. But the imaginary part is the sign. So you get 2 times the sign divided by, difference is 2I times the sign. Right? So the result is 2 sine A divided by A. So this is minus I dA to the power of n sine A divided by A. Now do the derivatives yourself. No, I mean, sine A over A is the spherical Bessel function of the first kind of 0th order. And this satisfies lots of recursion relations that we can use. So this is little j0 of A, and its first derivative, for example, is just minus j1. Second derivative is something else, and so on. So we can easily express all these mu integrals here in terms of Bessel function, spherical Bessel function. I wanted to be a bit faster, but let's see. I have a PhD committee meeting at 4 p.m. So. The spherical Bessel functions. Satisfy this recursion relation. Isn't this pretty? And they satisfy this recursion relation. For the derivative jn prime, this is n over z times jn of z minus jn plus 1. They are so nice. You see, suppose you start with the first derivative that you now have to apply here. This leads to a j0 prime. The j0 prime, because this vanishes because of the n here, is just a minus j1. Okay, so j0 prime is j minus j1. But now we need a second derivative. So we need a j0 double prime. So now we need j1 prime. This is going to be 1 over z times j1. So it's going to be j1 over z divided by z minus jn plus 1. So this is j2 of z. So this gives this beautiful combination of Bessel functions, decorated with a minus sign, which is cancelled by minus I to the power of 2. So in other words, this thing, the scalar product we wanted to know, and of course I forgot a factor of 2. Gives me a factor of 2 from here, a factor of 2 pi from here. So what remains is a 1 over 2 pi squared. Now without parentheses. Then we have an integral 0 to infinity p delta of k And then we have the result of the second order derivative without the minus sign. So we have J1 of Kr divided by Kr minus J2 of Kr. And the whole thing integrated over dk. Okay? Later we are going to split this again, but okay. So in other words, once you know one power spectrum, right? The power spectrum for the density fluctuations, then you can calculate these. You can calculate this function here. Now, it's late, I know. One more little thing. Of course, we need the other scalar product as well. So we need to project the P1, P2 on the perpendicular projector as well. This is going to be really easy, because all that changes in comparison to above. I'm now copying the first line with one slight change. Instead of k to the 4 p psi, I'm right away writing p delta. I'm now writing 1 minus mu square instead of mu square, right? Because the perpendicular projector is the unit matrix minus the parallel projector, and this is where this 1 minus mu square is coming from. The integral over the 1 just gives you J0, 0th order Bessel function of the first kind. The mu square you already have. So this is going to be 1 over 2 pi square, 0 to infinity, p delta of k, J0 of kr minus that result. So plus J2 of kr minus J1 of kr divided by kr dk. Final thing, I promise. Look, J0 plus J2. Set n to 1. This gives 3. This is a 3 times J1 over Z. 3 minus 2 minus 1 is 2, right? Now we know both of them. Bye-bye. No. Yes. How right you are. Yeah, the final trick is going to come. Good? All right. This was just to show, right, all the information that we need to know, the statistical information is stored in the density fluctuation power spectrum, and we can get all the components of the momentum covariance matrix just from these two functions, right? This one and the other one. Number 2 in almost all cases that we are going to study in cosmology, our initial phase-space distribution of momenta and position is just the Gaussian in the momenta and the flat distribution in the position. This is an approximation which is almost always very, very good. If this is not the case, we need to go back to the full expression which contains the d hat operator. But yeah, most of the time you won't notice that it's there. Very important. So what do we have now? We have an initial phase-space distribution, number one. We have Green's functions for the particle trajectory starting at any point in phase space, number two. Number three, we have a complete expression for the covariance matrix as we need it. Next time, we use that. Do you have questions? If your only question is, when do I get out of here? Now is the time. Choose. Choose. Hello.
I am Janindri. So because of a visa issue, when I got my application late, so I just arrived on Friday, and I wasn't
Welcome.
able to attend your classes in person, the previous classes. So would it be? I really want to take this course. Would it be? Would I be able to manage, and would it be possible?
To continue with the course?
Yeah.
Yes, of course. So there is a web page for the course, which I can send you the link when you send me an email, and then I just return this link to you. And then you find lecture notes of everything we have done so far. And maybe you can have a look at those, and then if you have questions, we can talk about them.
Okay, because I haven't received my student ID because of the IT shutdown. I am not sure if you're aware. I won't be getting my student ID for another 2 weeks.
Then I send you a PDF file for the lecture notes.
Yeah, so like I'm told to contact all my professors and ask them because I can't access Moodle. So
All
that
right.
is a problem.
Okay, yeah. Unfortunately, this is quite common. So I send you a PDF file then, and then we can proceed like that.
Yeah, and I also wanted to know, is it a considered an advanced level course? What would be my prerequisites that I would have to know to be able to take this course? Or
Just Hamiltonian mechanics.
okay. That's good.
Yeah.
I
So
have actually watched some of your lectures on YouTube earlier.
you did.
Yeah.
I feel honored.
So when I joined, I was like, I really want to take your course. And my only worry was I knew I was going to miss 1 month. So it's a little hard to catch up on everything that I missed. Yeah.
No problem. So of the last lecture, there's a complete video. Of other lectures, there's only part of the video. But there are lecture notes in any case. And so I think with them, you can easily follow them.
Okay. Yeah.
Just send me a mail and I'm going to return this to you.
Okay. Yeah. Thank you so much.
You're most welcome. Daniel.
Konzeptionelle Frage. Warum können wir das überhaupt machen?
Warte mal, eigentlich nicht mehr. so ungefähr 2 Minuten, weil ich dann eben zu dieser Betriebskommittee muss.
Kann ja auch eine E-Mail schreiben, das heißt.
Warte mal,
Also was ich nicht verstehe ist, dieses Skalieren von dem Potenzial ist nur definiert ideal zusammen. Jetzt ist
nö, das sind nicht in der Idee. Wir nehmen nur an, dass der Impuls beschrieben werden kann als Gradient eines skalaren Feldes. Und damit ist alles erledigt. Ja, dann wissen wir von der Kontinuitätsgleichung, dass sie eine Poisson-Gleichung erfüllen muss und so weiter. Aber was wir hier verwenden, ist nur, dass wir den Impuls durch einen Vektor, durch ein skalares Potenzial. Das ist die Aussage hier. Ne?
was könnte, wäre jetzt, wenn wir quasi zwei Teilchen am selben Ort haben, unterschiedliche Geschwindigkeiten?
Gibt's nicht. Gibt's nicht, weil wir noch auf der Anfangsfläche sind. Das heißt, die Störungen sind schwach. Und das heißt, noch ist die Zuordnung von Impuls zu Ort eindeutig. Später ändert sich das, ne, wenn der zusammenströmt. Aber im Moment sind wir noch in der linearen Näherung. Und weil die gesamte Hyperfläche, Entschuldigung, der gesamte erste Schnitt durch den Phasenraum zu beliebig früher Zeit ist, können wir das an eine Zeit verschieben, zu der das auf jeden Fall noch gilt. Und dann von dort aus anfangen.
Das heißt, es geht wirklich nur am Anfang.
Das geht nur am Anfang. Später geht es nicht mehr. Ne? Dann hat man tatsächlich ein mehrwertiges Geschwindigkeitsfeld, zumindest in einigen Orten. Und alles geht kaputt und so. Aber das ist gerade der Witz. Ne? Wir verschieben die Anfangsbedingungen zu einer Zeit, wo wir sie unter Kontrolle haben und schauen dann die Entwicklung nach vorne.